How do ML engineers use model evaluation metrics? Have you ever wondered how machine learning engineers ensure their models are performing at their best? One key aspect is the use of model evaluation metrics. These metrics help engineers measure how well their models work on specific tasks. They provide essential feedback on accuracy and effectiveness, guiding engineers to improve their models before they go live. First, engineers need to identify the type of problem their model is solving. Is it a regression task where they predict continuous values or a classification task where they predict categories? The choice of metrics depends on the task at hand. For regression tasks, engineers often relying on several metrics. Mean absolute error calculates the average absolute difference between predicted and actual values. This metric gives a clear picture of prediction accuracy without indicating whether the model tends to overestimate or underestimate. Another common metric is mean squared error. This metric averages the squares of the differences between predicted and actual values. By squaring the differences, it penalizes larger errors more heavily, making it sensitive to outliers. This is why many engineers prefer it during model training. Root mean squared error is similar but expresses the error in the same units as the target variable. This makes it easier to interpret. R squared measures how much variance in the target variable the model explains. Values closer to 1 indicate a better fit. When it comes to classification tasks, engineers often use different metrics. Accuracy measures the proportion of correct predictions out of all predictions made. Precision and recall are also important. Precision tells how many predicted positives are actual positives, while recall shows how many actual positives are correctly identified. The F1 score combines precision and recall into one metric, balancing both. A confusion matrix provides a detailed breakdown of true positives, true negatives, and false negatives, helping engineers diagnose model errors. Engineers also utilize the receiver operating characteristic curve and area under the curve to evaluate a model's ability to distinguish between classes across various thresholds. Cross-entropy loss is another metric often used during training. It measures the difference between predicted probabilities and actual labels, decreasing as predictions improve. These metrics are not just numbers. They help engineers compare different models or versions and decide when a model is ready for production. For instance, when developing artificial intelligence tools like chat-generative pre-trained transformer or image generators, such as DALL-E and Midjourney, evaluation metrics ensure that the models generate accurate and relevant outputs. Moreover, engineers must consider the ethical implications of their models. Evaluation metrics can reveal biases that may affect certain groups, prompting necessary adjustments. This is crucial for promoting fairness and responsible use of artificial intelligence. In addition, productivity plugins that integrate artificial intelligence models, relying on robust evaluation to deliver reliable assistance without unintended consequences. Overall, model evaluation metrics are essential tools for machine learning engineers. They help quantify model quality, guide improvements, and uphold ethical standards in artificial intelligence applications.